Hi everybody, I thought as a follow-up to the review I did on the DROK DC to DC converter module, I'd have a look at maybe a few little modifications to that. This is following some of the comments that I had. And the unit itself, the accuracy of the DC voltage reading on the LED display, there's no means of trimming that to improve the accuracy, so I thought we could maybe do something about that. Also, I thought it a little bit strange that you had the option either to look at the input or the output voltage. The output voltage, I agree, is good to look at, but the input voltage, you know what input voltage you're putting into the device. So I thought maybe it's better to use the second reading on the display to show the current, rather than the output current, that is, rather than the input voltage. So we'll have a look at that as well. And finally, I thought one nice little addition to this would be to have a on-off feature of the output voltage using a tactile button. So we'll have a look at that as well. Well, I'm sure you remember from last time the circuit diagram we had. There were two potential dividers, one on the output, one on the input, of a 30k and a 2k resistor, and they're tapping off a sample of the output voltage or a sample of the input voltage, feeding it to the microchip, and then with the tactile buttons there, they're displaying either the input voltage reading or the output voltage reading. So I thought one way of improving the output voltage reading would be to replace the 30k fixed resistor there with a combination of a preset and a fixed resistor to give you some trim capability, to trim the accuracy of the reading on the display. And then as far as the divider on the input voltage, I'm going to remove that altogether and then use the input to the micro to monitor the output current of the device. So in addition to that, we'll also have on the output some form of switching the output voltage to the output terminals on or off, and also it'd be nice to see if we can have it defaulting at off when you first power the unit on. So let's have a look at the additional circuitry I'm going to add to this module. I'll probably do it on a second PCB which we just bolt onto the back of the existing DC to DC converter. Right, well, here's the circuit I've put together today for this little project. It's basically in two parts. The first section here is to do with sensing the current output from the DC to DC converter and giving us a voltage which we can use to give us a reading of the output current. And the second part is to do with a soft switch to switch on and off the output from the DC converter. Now, the only additional items I've put on here are a few resistors, potential dividers, to drop the voltage down for the little micro on the DROK DC DC converter to give us both the voltage reading and the current reading. So if we look first of all at the current sense part of the circuit, I'm using a MAX 4080. It's a little high-sided current sense IC, and these particular chips come in three variants. The one I'm using today is the T variant, so you need to look for the letter T at the end of the number. So this one is the MAX 4080T, and I've just indicated at the top here the differences between the variants. You have the F, T and S variants of this IC, and the differences are the full-scale voltage sense that it can provide on the output pin, which is pin 5, and the gain, internal gain of the amplifier. So if you look at the T version, it's capable of giving us a full voltage sense up to plus or minus 250 millivolts, which is more than sufficient for our needs today. But more importantly for us, it gives us a gain, internal gain of times 20. Now you'll see here that I've used a 0.05 ohm resistor, and if we put 1 amp through 0.05 ohm of resistor, we get 0.05 of a volt. If we multiply that then by 20, it gives us 1 volt voltage reference coming out, which we will then use to measure the current. In this case, it means that we simply use the voltage coming out of the reference output of this IC to give us the representation of the current being drawn from the DC to DC converter. Now I'll just quickly mention the resistor networks I have here. First of all, the output voltage from the current sense IC at pin 5, I've put across a potential divider network here, a little 100k 15 turn preset, 47k and a 10k resistor. The 10k resistor, I've made that of 0.1% tolerance. All the other resistors in the circuit are 1% tolerance. The other voltage divider network here forms the other half of the potential divider network for the DROK DC converter to give us the output voltage reading. And basically what I've done is I've replaced what was the 30k ohm resistor on the DROK with a 27k and an adjustable 5k preset, and that gives us a little bit of trim to adjust the accuracy of the voltage reading. And you'll notice that the ratios actually of the divider network, originally on the DROK DC converter we had a 30k and a 2k, and that gives a ratio of 15:1. So we keep the same ratios here, so you see that we have 100k and a 47k, so that gives us 150k with a 10k in the bottom end there. So again, we're maintaining that ratio of 15:1, and the reason I've increased the values here is to reduce the load on the output of the current sense IC. Signals from these divided networks, the voltage one goes to pin 2 of the little micro on the DROK DC converter, having already moved the 30k resistor on the module, and this one here, which is sensing the current, goes to pin 3 of the micro on the DROK, and that gives us an indication of the current output of the load on the DC converter. Now the second part of this circuit is to do with a soft switch on the output of the DC converter, which means that we can set the output voltage before switching the output to whatever you're connecting the DC converter to. So this is acting as a switch, and for that I'm using a P-channel MOSFET. The P-channel MOSFET I'm using here today is a Vichy SUD50P-08, a relatively cheap P-channal MOSFET. It's a surface mount component. It's particularly good for this application because it has a forward on resistance source to drain of between 6 and 10 milliohms, very low. And the other advantage is it can handle currents anywhere up to 50 amps. Now the only point you need to watch out for on this is the maximum source to gain voltage. On this particular chip it can handle up to plus or minus 20 volts, so we need to put some sort of protection on the source to gate drain, and for that I'm using a 15 volt Zener, so it just clamps the maximum voltage across the source gate to 15 volts should anything go higher than its maximum rating. Now this particular P-channel MOSFET is simply acting as a switch, and all you simply need to do is take the gate down to ground to switch it on. And we're doing that by using a little NPN transistor, in this case a 2N3904, which we're driving from a little bistable circuit here. So when the transistor turns on, the MOSFET turns on, and the output voltage is fed to whatever circuit you connected to the DC to DC converter. Now this part of the circuit here forms the little bistable that drives the transistor, and it's this that is controlled by a little tactile switch here. So the tactile switch is simply acting as the on-off to control the P-channel MOSFET. And basically what it's doing is we're using two inverters there with positive feedback, which is the R2 resistor 5.6k, as a little bistable latch. And the idea is that if the input on pin 1 there is high, that is low, that is high, and if that is high, then if you feed it through another inverter, that's low, which means the transistor is off. If we flip the little bistable into the opposite state, pin 1 goes low, that goes high, that goes low, which means the output here goes high and turns the transistor on, turning on the MOSFET. Now, when we first switch the power on, and in fact for this particular IC I'm going to use the plus 5 volts, which is available on the DROK DC converter. I'm just going to tap off of the little 5 volt regulator, and I'm going to put a 0.1 capacitor there. There's a little decoupling. When we first switch on, the 5 volts is fed to the inverters, and this capacitor here has got no charge on it, therefore it's effectively at ground, which means that point through R1 is at ground, so that's at logic 0, which means that's at logic 1. Positive feedback feeds that 1 to that gate there, which means the output of that is low, which reinforces the fact that it was low to start with. So it latches in that state where it means that the output here is high, and if that output is high, that output is low, which means the transistor is off and there's no output from the circuit. So it means that when we first switch on, that the MOSFET is held off. If we then momentarily press the little tactile button there, it connects the input of that inverter down to ground through the 47 nanofarad. So that goes low, the output goes high. You've released the button by now, the output's gone high, which means that the capacitor now will start to charge. A high output on the input there will cause that output to go low, which means that this output here, this inverter goes high, switching on the transistor, grounding the gate of the MOSFET, turning on the MOSFET and giving us our voltage out. So the circuit is now switched on, and the little bistable there is latched by, again, the positive feedback with the resistor R2. So what we have now is the little bistable there locked into that state where pin 1 there is low, but the capacitor there has now been charging through the R1 resistor because that point is high. So the next time we press the little button there, the positive charge on that capacitor is fed to pin 1, which takes that high. As soon as that goes high, the output goes low. That output low means this output here is high, and you again get positive feedback with that resistor R2 enforcing the high voltage on pin 1 and locking it into that state. So that's high, that goes low, the transistor now turns off again, removing the connection from the gate to ground, and the MOSFET turns off. So it's a little bistable circuit there that we're using by simply using a couple of inverters or NOT gates, and following that with another inverter to give us the correct signal on the transistor to drive that transistor there. Now the particular inverter IC I'm using here is a hex inverter. I'm using the 4069, but you can use any sort of hex inverter IC for this project, and the components themselves are not overcritical. The only thing you need to watch out for is that the relationship between R1 and R2, R2 has always got to be at least 10 times smaller than R1. Otherwise you'll find that the circuit may go into oscillation. And the other nice feature of this circuit is the fact that the little CR network here also provides some debouncing function for the little tactile switch. So you can use a very cheap switch because you've got the debounce feature there as well. So I think the next thing we'll do now is we'll build this circuit, and we'll connect it to the DROK DC converter and see how it works. Now all the features that I've described on this circuit here today. You can use it with other applications, so you have a nice little sort of current sense circuitry there, and this sort of self-latching on-off power switch, soft switch there, which can be used with many circuits. So it's a little thing you can use on other projects in future. Well, we need to remove the 7-segment display there so we can gain access to the components beneath that. So the first thing I'm going to do is unsolder this carefully using some solder wick and a desoldering tool to solder this display. So let me do that first, and we'll come back and we'll have a look at the circuitry underneath and the changes we need to make. Right, well, I've now removed the display, and we can clearly see now all the components underneath that module. So what I'll do now is I'll just zoom into this area here and just indicate the components that we need to remove from the board. Right, well, here we have a closer look at the area of the board that we're going to make a few changes, and in particular the potential divider networks that are used to monitor both the input and the output voltage and feed the signal to the microchip. R13 and R14, R13 is the 30k, R14 is the 2k resistor. They make up the potential divider to sample the input voltage and feed it to the microchip. We'll remove both of those resistors. On the other side of the microchip we have R15 and R16. R15 is the 30k, R16 is the 2k, and they make up the potential divider to monitor the output voltage. And what we're going to do there is leave the 2k resistor in place, that's R16, and remove R15. While we have the close-up of the board, I'll just point out there we have the 5-volt regulator IC, and the right hand pin there is the plus 5 volts output, and we're going to tap off of that to feed the logic hex inverter IC on the upgrade module. So what I'll do first of all is I'll remove the resistors from this board and tack some wires on to connect through to the upgrade module. So let me do that and we'll come back and have a look. One thing I should point out is that the wire I'm using here is small gauge multi-strand wire. It needs to be light and flexible so as not to pull any of the print off the board. Now the next thing I need to do is to remove the output terminal block here, which we're going to reuse on the upgrade module. So I'll just unsolder that from this board. The final step now is I'm going to put a socket there for the LED display to plug back into rather than solder it back into the board. And what I'm going to do for that is I'm going to use a 14-pin IC socket. I'm just going to cut down, and then I'll solder that in at either side, and the 7-segment display will then just plug into that. So let me do that. The socket has now been soldered in, as you can see, and I'll now plug the 7-segment display back onto the board. Right, that's complete for this stage of the project. Well, here are all the components for the little project today. I decided to make a small PCB for this module, which will be bolted to the original DC to DC converter by using some plastic spacers here, standoffs, and then it'll be screwed onto the main DC to DC board with the steel screws there. So the components we have the IC here. This is the current sense IC, the MAX 4080. There's the NPN transistor using the 2N3904. We have a 47 nanofarad and a 100 nanofarad capacitor, the only two capacitors on the board. There we have the tactile switch we'll be using, and I have a little red knob here which will clip onto that tactile switch. This component here is the current sense resistor. This particular one is one I had in my workshop here, which is 2 watts, but you don't need one of this physical size, and you could obviously make your own with wire, I would have thought. Anyway, that's what I'm using today. There we have the logic IC, which is the hex inverter, the 4069. There is the P channel MOSFET, which will be soldered there onto the board, and there's the little terminal block which we removed from the original DROK DC to DC converter module, which I'll then resolder on this board at the end here. And finally we have 8 resistors. They're all 1% tolerance, apart from the last one there, which is a 10k 0.1% tolerance. And there's the 15 volt Zener diode, which we'll be using to protect the source gate junction of the P-channel MOSFET. The one I'm using here is a 1.3 watt 15 volt Zener. So there we are, there we have all the components. So I think the next thing we'll do, we'll have a look at placing the components on the board itself. Just before I start soldering on the board, I'm going to secure it with a couple of pieces of blue tack so it doesn't move about. Now the next thing I'm going to do is tin the areas where we're going to mount the surface mount components. So the 2 ICs, I'm going to tin those areas there, and also where the P-channel MOSFET is going to sit as well. So I find this is quite useful to do when you're mounting surface mount components onto a PCB, to tin the board first. So I'll just show you how I do that. And I'm going to use some very fine solder, some multi-core solder here, which I'm going to use for this particular job. And in addition to that, I'll be using some desoldering wick. I will now just tin the areas of the board that I mentioned. So here is the MOSFET, so I'll just tin this area here. And then the ICs. You just need to be careful when you're doing this, because the spacing is quite small on the ICs. There we are. Right, once you've tinned the board, you just need to clean it up a little bit with some solder wick. So we just take off the excess. And same for the ICs. Well, there you can see now that I've tinned the area of the board for the surface mount components. So I think the next thing we'll do is we'll solder on those 3 surface mount parts now. Right, the first thing we'll fit is the P-channel MOSFET, and I'll just dab the connections with a flux pen here. I'll just tack one end of the MOSFET. Once it's in its place, just hold it down with your finger firmly on the board, and then just heat up the solder and tack one of the pins on. Okay, once you've got one pin tacked on like that, it holds it in place, so you can then solder the other pins of the MOSFET. And then finally just touch up the first pin that you soldered. Right, next we'll solder the logic IC to the board. Again, I'll just touch the pins with a flux pen, and then we position that correctly onto the board. Once you've got the IC there positioned correctly on the board, making sure that you have pin 1 adjacent to the little round dot I put there on the board to signify the pin 1. And the way you identify that on the IC is you've got a chamfered edge down that side of the chip, and pin 1 is on that corner there. So what I'm going to do now is just hold it down again with my finger, and then just tack one end, put a bit of solder on the iron, and then just tack one end of the IC. Okay, I've just tacked that one end now, so the IC is held in place. So what I'll do now, I'll go around and just solder all the other connections. Right, well, I've now just positioned the current source IC there on the board. Again, making sure I have the correct orientation. The little dot there signifies pin 1. And I'm just going to hold it down while I solder one of the pins, and then we can solder the rest. Right, well, I've soldered all that there now, so the two ICs are now soldered on the board, as is the P-channel MOSFET. So I think the next step is to install all the other components on the board. I'll do that, and then we'll have a look at the completed board before we attach it to the DC to DC converter module. Here we can see the completed module now with all the components installed. I've marked on the top of the board some of the connection points. So here we have minus and plus in, which connect with a wire straight onto the DROK DC DC converter module, as do the output terminals here. We've got out minus, out plus, go straight to the DROK. And then we have 1, 2, 3 other connections here, wired connections. We have a plus 5 volt supply coming from the DROK DC DC converter to feed the logic IC on this board, and then we have I and V, and wires going from these 2 points will go to the little microcomputer on the DROK board to give it the signals to measure the output voltage and output current. And then the terminal block at the end, that's where the output will now come from, and the switch there switches the output power on and off. So let's now hook up this module to the DROK DC-DC converter and then test its operation. Well, here we have the two completed boards, and the next thing is to marry the two boards together. I'll solder the 3 wires onto the points on the board, 5 volts there, the current sense there and the voltage sense there, and then I've put some tin copper wire standoffs for the input and output that go to the input and output on the DROK DC-DC converter board, and that will slot in these holes here. You'll see there, there and there. So let me marry the two boards together and solder that in. Here's the final project. You see we've mounted the little upgrade board onto the back of the DROK DC-DC converter. There's your two trimmer pots. The first one there is for trimming the voltage reading, and the second one there is for trimming the current reading. The main difference now in the operation is pressing the I button, which was previously the input voltage. That now shows you the output current, therefore I signifying current, and the 0 is still giving you the output voltage, with the added benefit of being able to trim that voltage with the little preset to get the correct reading on the display. So there we have the module, and I'll just give it a quick test with the power supply and with a load on it. I've got the module now hooked up to the power supply and the electronic load. I'm feeding it with 30 volts, and the electronic load here will show us the output voltage and the load current. So let me just switch on the power to the module. At the moment you can see we've got the DC to DC converter set to 10 volts output, and if you look on the electronic load at the moment, you can see that the output voltage is 0, and the reason for that is that by default now the output is switched off, and when we press the little tactile button here now, it turns the output on, and here we can see it's giving us the output voltage reading showing 10.15 volts, whereas the display is showing 10.0. So I can now adjust that display with the little preset pot there to give us the same reading on the LED display as we have here on the output meter. So let me just trim that port. I've adjusted the preset on the bottom board now, so we're getting a reading now on the LED display of 10.1 volts, which is exactly the same as we have here, 10.1 volt. What I will do now is I will set the electronic load to give us a load of 1 amp. At the moment I'll switch the little DC-DC converter off by pressing the tactile button there, so switch off, and you can see now that the output voltage has dropped down to 0. I'll switch the load on, so I have the load switched on at 1 amp. So if we now press the tactile button, and there you can see now we have a load of 1 amp. The output voltage here is showing 10.04 of a volt. That's still showing us 10.1, but again we can trim that with the little preset. It's to take that down to a 0 under load. And if we now press the I tactile button at the end there, it should show you the output current. Now at the moment it's showing me 1.6 amps, whereas in fact we only have a load of 1 amp. So I'm now going to adjust the other preset so that this now reads 1 amp. So let me do that. Right, well, I've adjusted the preset there that sets the current reading, and we're now getting a reading of 1 amp, which is exactly what we have on the electronic load. I'll just press the button to read the output voltage. It's 10.1. Let me just trim that. So it's now reading 10.0, which is the same as we have on the electronic load. So them two match up now. Just check the current again. 1 amp. I've set the DC-DC converter now to 20 volt output. The load is still 1 amp. There's no output at the moment. If I press the tactile button, you'll see the voltage come up, 19.96. You can see it's hovering between 20 and 19.9. Press the current display now. Again we're showing 1 amp. Well, I hope you found this little project of interest. At the end of the day, I did quite like the ability to switch on and off the output power with a little tactile switch, and also to trim the accuracy of the voltage reading on the display. The current reading, I found that there was some slight errors above and below the 1 amp reading, and that was due mainly, I think, to the software that's programmed into the little microchip on the DROK board. But other than that, it worked quite well, and you could actually put a little test pin on pin 5 of the current sense IC and measure that with a voltmeter and get a true representation of the output current. But all in all, worked quite well. I will put some links down below where you can download the artwork for the PCB and a copy of the circuit diagram and the parts list. So if you found this of interest, please give me a thumbs up. Thanks for watching, and I'll see you all again next time. Bye for now.